I'd like to thank the organizers for inviting me to give this talk. It'll be about monotone mixtures of monotone, boolean, and tensor independence. And I'll start with a bit of background in terms of mixtures. I'll start with the work of, the classification of universal and natural products of a bunch of people, Sherman, Spiker, and Meraki, where the conclusion is that, well, we have, under some conditions, we have tensor, boolean, free, and monotone independence. We also have anti-monotone, but it's kind of the opposite twin, or of monotone. And then in terms of mixtures, we go to 2002 with the work of Moltowski about lambda independence, and he considers mixtures of free and tensor independence. Later reconstructed, rediscovered by Spiker and Vazquez-Becerra in 2016, although they call it epsilon independence, in which you have a matrix epsilon, which you encode the type of pairwise independent relations in your algebras. And then in 2005, we have Vazquez-Becerra with BM independence, and he considers mixtures of Boolean and monotone independence, essentially replacing the total order that you ask in monotone independence by a partial order. And then we also have this paper by Kula and Vazquez-Becerra where they consider Boolean and free. And then there are some other mixtures that appear in different theories, like traffic freeness of Camille Mail, of bifreeness of Vazquez-Becerra of byproducts. But also there is the work of Jacob and Liu about mixtures of free, monotone, and Boolean independence. Okay, the algebraic framework that I'm departing from is just the usual algebraic framework in non-probability, non-commutative probability, where you have a pair, where you have a complex algebra and a unit of complex algebra and a linear functional there that goes from a linear functional that maps the identity to 1. Through the talk, we'll assume like I have a family of solo algebras indexed by set V and a D graph, which is just a directed graph on my index set. I also make the convention that by an alternating product, I mean a product of the elements from my algebras with the condition that adjacent elements come from different algebras. That's it. Okay, and then as an example, a very simple example, kind of the motivation of this work is that I just take a complex Hilbert space K, and then I consider it's the tensor product with itself. Okay, and then I just have the usual construction where I find the inner product just as the product of the inner products. And there is one condition more, that I have a distinguished unit vector on K, and then I just which I call here eta, and then I have z eta, yeah, and z is just the tensor product of those two. And then to have non-commutative probability space, well, I define this linear functional, which is simply the vector state associated to eta. The thing about this example, like this very basic example, is that in this non-commutative probability space, well, it contains operators that are already in Boolean, monotone, and tensor independent. And the examples are very simple. The only thing that I need to consider, or some notation, is that, well, I denote by I the identity operator in K, and P is just the projection on my distinguished unit vector eta. And then there's some properties about this projection. Basically says that here that if I have two operators, and then I put a P in the middle, and I consider this inner product, which is the vector state associated in BK, then it basically breaks out into these two guys. Okay, and if I conjugate a operator by P, then I have this relation here. Okay, those two basic facts allows you to prove that, well, if you consider A tensor P and P tensor A tensor P and P tensor B for any A and B, well, those two are Boolean independent with respect to my vector state. Here I just put, well, what does that mean? That means basically that if I have a mixed moment on these two operators, then I'm able to calculate that mixed moment in terms of the rule for Boolean independence, which I will specify later on in abstract terms. And I just put here this mixed moment to make an example of what's going on here. Okay, but then if I replace the first P with an I, then I get monotone independence. Okay, I take the same mixed moment just to exemplify that the way I compute the mixed moment changes as with respect to my notion of independence. And the same for tensor independence. Now that I have two, instead of having two P's, I have two identities there. Okay, so what I've shown is an example of how you, in a space, you can have a monotone tensor and Boolean independence. Okay, so here's just a summary of what I said. When you have on both sides P's, then you have Boolean independence. When you have an identity and a P, you have monotone, and when you have two identities, you have a tensor. Thing about this basic example is just basically exemplifies everything that like you can increase you can replace K by different Hilbert spaces, and then you just consider the tensor product of those Hilbert spaces. Yeah, so this is the basic example, and then let's suppose you have some other Hilbert spaces, each one with a distinguished vector, and each one has well, a vector state associated to it, which is just our linear functional that makes this pair a non-commutative probability space. And again, I have an identity operator in each of my Hilbert spaces and the projection onto my distinguished unit vector. I consider, again, the tensor product of my Hilbert spaces and the tensor product of my unit vectors. Okay, and now the thing is that this basic example basically encodes a framework in which I can define a notion of independence with a specified pairwise independence relations. And the way we do that is that we will have a D-graph that will encode our pairwise independent relations, and I'm going to embed my initial bounded operators into the tensor product, and it's basically the same idea as I did before. Before I only had two, and I had A tensor P and P tensor B. Now I will have more. So in my tensor product, at the position I will just put the operator I'm taking from BHI, and then in the other entries, I will put either IJ or PJ depending on a D-graph GN. Okay. It'll be basically the same idea as I had with just two and capital N equals 2 in the previous example. Well, this construction gives me a representation of my initial non-commutative probability spaces into the tensor product, and that's it. That's very easy to see or prove. The thing is with this construction is that it doesn't matter what I put on the rest of the entries. If I focus on the algebra AI, which is just the image under my homomorphisms on BH, if I look at AI and IJ, well, it all depends on the permutations that I have in the entries IJ and JI, what the notion of independence they will satisfy. Just think about the case of 2 when I have A times P and P times B. Yeah, so it really matters that. And then if I have these conditions, then these two algebras, well, the image in BH are Boolean independent. And then if I have Pij equals to Ij and Pji equals to Pi, then Ij is monotone independent from AI is independent from Aj, and then I have tensor independence. Okay, so basically I'm not doing anything more extra. No, I'm just saying like I have an example, I can increase this example to any dimension. But the thing is that, okay, what extra I'm having here? Okay, what's extra here? Well, it turns out that the graph basically determines the pairwise independent relations that I have. It means that basically with our notion, we prove that these notions can coexist in a way. Okay, you can specify the pairwise relations, and here's an example of a graph. Um, okay, so we do this by, because it dependent on the edges. Yeah, so here, if you have no edge, then that means no edge between any algebras, that means Boolean independence. And that's why here, for this graph, represents that A5 is Boolean independent from A2, A1, A2, A3, and up to A4. Monotone independence is represented by a directed edge. So here I have A2 is monotone independent from A3, and A1 is monotone independent from A3 too. A2 and A4 are tensor independence. Here I merged two edges, one going from A2 and another to A4, and another one going from A4 to A2. Okay, and here, well, I guess in this framework, basically, one thing that you gain is that one condition that you drop in terms of the universal products or these conditions is that basically you're dropping associativity. Okay, and that can be seen in this graph. Well, in this graph, because here usually associativity says, well, you have an algebra here, and then you have an independent relation between these two, and then you ask the same independent relation between A1 and A2 and A3. Okay, that's kind of the linear order that you require for monotone independence. But here it says like you don't need that linear order. You could switch this error, and instead of going from A1 to A3, you can go from A3 to A1. And basically you're dropping associativity there. And you're saying that's still okay. Like a pairwise, I get a framework in which pairwise independent relationships are okay, even though if they don't satisfy associativity. Okay, and then one first result is that if we go back to the construction we had, this family of algebras are BMT independent. I haven't said that is, but basically what it means is that we found a consistent way of computing mixed moments that includes Boolean, monotone, and tensor independence. Okay. Let me go back to the algebraic framework. This is just a reminder of the notation I'm using. I have some algebras, a D graph that encodes my pairwise independent relations, and the notion of an alternating product. And in terms of alternating product, these are the definitions of the notions of independence. For Boolean, for any alternating product of elements of my algebras, well, that breaks down into the product of the linear function evaluated at each variable. For monotone independence, we have two rules. And I should emphasize that, well, we need a condition that is an additional condition, that is that we impose a total order on the index at V. And then we have two rules. One of them reduces the length of the word of the alternating product, and the other one is similar to Boolean independence. Here the point is that whenever I have some conditions, I can reduce the length of my word, and then when I have another conditions on the indices, these i's are the elements where the a's comes from. So A1 comes from AI1 and so on. But anyway, here I have a condition that if I have an element which the adjacent elements are less than the element I'm looking at, then I can reduce the length of my word. And if I have a condition of decreasing, it's really decreasing on the indices, and then it's really increasing indices, then the product breaks into the same rule as Boolean independence. And now for tensor independence, here I made this in purpose. Here I have only a kernel of I, but what it means is that I basically group the elements that come from the same algebra. I multiply them in the same order that they appear in the original product, and then I compute those products. Okay. The reason why I put this is because my definition of BMT independence is essentially at the algebraic level is basically I replace this kernel by some other object that will depend on the graph G. Okay, so what's that kernel? Okay, the kernel is of I. If I have a function that goes from M to V, then I say that well, I identify that function with a tuple, and then I'm going to create kernel of I, so a partition of M, such that defined by an equivalent relation that says that, well, K and K prime are related if the function I has the same value of those two guys. That means IK equals IK prime. So that's the equivalence relation that defines the kernel of I. Basically, I'm just grouping elements that come from the same algebra. Now, for the kernel of G of I, so I have the same condition. I have, again, an equivalence relation defining this partition. And I ask, again, that, well, K is related to K prime if and only if IK equals to IK prime. But then I have a technical condition here that basically says that, well, suppose that K is less than K prime. And then I have an element L there, such that IK is not equal to IL. That means like the elements that represent, the algebras that represent are not the same. Okay, that's the only thing that means. So these two guys are related here if this condition holds, but I ask that this guy here is an edge of my graph. Okay, okay. So because I am requiring an additional condition here, it's automatically that the kernel of I is just a refinement of the kernel of I. Okay, and then my definition comes very easy because I will say that the subalgebras are BMT independent if they satisfy this relation. If the mixed moments breaks down as according to the kernel of GI. And then we can see that, well, for specific cases of my graph G, I will recover boolean, monotone, and tensor independence. Okay. Okay, and again, this is just a reminder that I can construct operators. I define the pairwise independent relations that I want to impose on them, and then I will have a rule to compute their mixed moments according to this kernel of I. Okay. So I'll just spend a few minutes explaining these things about the kernel because basically it's the main object in terms of my definition. The kernel of I, as I said, it just puts together elements that come from the same algebra. And if I have, let's say, a tuple here, well, I have a partition that basically only joins two elements if they have the same value on my function I. And if they have different values, then I don't join those two guys. Okay. What about the kernel of GI? Because that's the main thing in my definition. And here, let's say, for example, I take the block 1 and 5. And what's the technical condition about the graph is that, well, I look at the elements that are in between. So in this case, it'll be 8, the block that corresponds to the number 8, which is here, and the block that corresponds to the number 4. And as I said, the kernel of I is the kernel of G of I is a refinement of the kernel I. 1, 5 is a block in the kernel of I, and then that block will be partitioned into 1 and 5 if either the edge that goes from 8 to 1 is not in G, or the edge that goes from 4 to 1 is not in G. If that condition fails, then I split my block. And then, yeah, I can do the same for the other. I do the same for the other blocks. And again, if there is an edge that is not there, then corresponding block will be partitioned into the smaller blocks. Okay, and it turns out that, well, if I go back to the construction I had, when I said these algebras are BMT independent, I meant that to say that they satisfy exactly this way of computing mixed moments. Okay, just a reminder of what the notion of independence are. It's clear that if G is the complete graph, then I'm not partitioning my kernel into smaller sets. So this proves that if G is a complete graph, then the kernel of G always equals the kernel of I. And then I obtain tensor independence. If G is the empty graph, then this technical condition about the graph is never satisfied, and everything gets splitted. And well, for monotone independence, a little bit trickier, but it's an argument there. And basically, the main technical thing there is that I can compute it as if I lack some edges, then I can compute the mixed moment either removing the ik element. Okay. Yeah. So this is the main one technical point, that basically this kernel of G of I, there are some conditions in which I can remove a subset of my elements, and if I remove that set and I compute the kernel of G of I of the remaining A's, then it doesn't change. I should point out that usually for monotone independence, they require some conditions at the level of the algebras, but here we are able to prove that you don't need that. Usually what they do is that sometimes you say, well, the operator satisfy a relation, and then I make a quotient so that I don't have problems computing mixed moments. And the way I start computing mixed moments in this, this recursive formula, because I might take out a different k, and then I need to prove that if I remove another k, then it will be consistent. Anyway, but here we don't need that, and that's encoded in these two technical lemmas. Okay, BM. We also recover BM independence, and it's essentially the same rules as monotone independence, just that now we only require a partial order, and then there are some other cases in which either we can reduce the length of the word, or we break it into the product of all the elements in my word. But the idea is the same, so I will not go into that. And then the last part in terms of what, well, one of the last parts in terms of what we did is that, okay, so we have this general rule to compute mixed moments that encloses boolean, monotone, and tensor independence, and we were able to prove a central limit theorem and a Poisson type central limit theorem, and it all relies on combinatorics. And in that sense, the main object is the nesting crossing graph, that if once I have a partition, I will consider what we call the nesting crossing graph, and it's just a graph where the vertex set is just the blocks of the partition, and the edge set, I will have an edge going from a block W to a block V, if either V is nested inside of, well, W is nested inside of V, or V and W cross each other. Here I have an example of a partition. You can see that the blocks corresponds to 1 and 5 crosses each other with the block 2, 3, and 7. So that creates a double edge there. 4 is nested inside 2, 3, and 7. So that's why I have this edge. Well, no, this edge here, but it's also nested into 1 and 5. That's why this edge is here. And 6 is only nested inside 2, 3, and 7. If I have a function, additional function that satisfies the kernel of I equals pi, that basically means that the tuple evaluated at these sets, it's constant in each set, and for different sets has a different value. Then I also okay, this is the nesting crossing graph. This I denote by g pi, and then I also denote by g pi I when I evaluate the blocks at the function I that satisfies condition the kernel of I equals pi. Thing about this combined graph is that, well, it turns out that the kernel of g of I is equal to kernel I. It means that it doesn't get partitioned if and only if g pi is inside my graph, my original graph. Okay. This condition here is basically when you expand in moments, it gives you the right degree of growth. Okay, here's another example. Okay, and then both the central limit theorem and the Poisson type limit theorem are reduced in our framework to count how many ways you can embed the nesting crossing graph in your pairwise independence relation graph. Okay, so here I put another example of another partition. Here is just a pairing. It had the same nesting crossing graph as before. That means that we don't have an injective relation from partitions to nesting crossing graphs. And this quantity here just counts how many times I can embed this graph in my original pairwise independent relation graph. Here you can see that this graph can be embedded only twice. But if I remove an edge, then only once, and if I remove another edge, then I cannot embed any longer my graph. This is just saying the same thing, I think, just with colors. Yeah, it's just essentially the same thing. I can embed this guy here only twice here. And then we are down to the central limit theorem here. So this quantity only counts here. Okay, so I have, for the central limit theorem, I have central random variables, unit variance, moments of all orders. I compute the mth moment. I'm saying that that m moment goes to, well, I consider all non-crossing pairings, this normalization constant that comes from this square root, and then here that basically says that how many times I can embed the nesting crossing graph associated to the partition, to the parent partition pi into my graph of independences. And then you can see that, well, it's with this graph argument, you can recover the central limit theorem for boolean, monotone, and tensor independence. Because if you have the complete graph, then it doesn't matter. You just pick values of your nesting crossing graph, and that will be embedded in your graph. If you don't have any edge, then you cannot do that unless you have a very specific partition and you have a similar argument with monotone independence. We also have a, well, a corresponding Poisson type limit theorem. And I guess my final comment here is that this is very sensitive in the sense that this result here says that if, let's say, if you have edges, the number of edges is less than n squared, and you have two pairs of algebras, or two pair of sequences of random variables, and you can, for each family, you have an independence graph, and then you consider the symmetric difference, then they will converge to the same thing if the number of edges in the symmetric difference is of order less than n squared. What that means is that, let's say, for example, you still get Boolean, the central limit theorem for Boolean independence, even if you have I don't know, n combinations that are monotone independence. And well, there is more in the paper, and I think well, there's some questions there, like how do you determine if the limiting measure is has compact support? No, you can prove that with this approach. You can give an argument that even with BM independence, you cannot get the semicircular law. And then, well, the idea to continue this work is somehow like, can we come up with an idea of vanishing of mixing cumulants, and of course, if there's in a framework that can mix all the notions of independence. Thank you.